Okay, it's very strange how only when I mention it's going to crash, it doesn't crash. It's odd. I don't know how I feel about it.
Like a sneeze.
Oh, yeah. I mean, yeah, it's like
I think
reverse.
recording after you share your screen doesn't break it.
Oh, interesting. Okay, maybe that's the answer right there. Cool. But yeah, just to get us started, we have our Big O demo lecture here. Sorry, that's not it. We have our Big O lecture here. Which I might as well put in Markdown, but that has a link to these slides, which I'm going to be presenting from, and you should have access to them too. And before we do even that, I was thinking, because I've looked at the slides and they're helpful, but Big O is a topic that, because it comes from a relatively academic part of computer science, it can come off as very high level and sort of like useless and theoretical. And I think we would all be well served by kind of walking into it in a little more of a casual, like colloquial way. So in order to do that, I'm going to, where do I have it? Just start with this notes on Big O, and next to this scratch pad, and I'll make this a little smaller. But yeah, so the core, so first of all, when we say Big O, we're talking about this thing called complexity analysis. Big O just happens to be a specific type of complexity analysis, the one we care about most often. But what is complexity analysis? So this comes from a really cool place. The person who invented complexity analysis, his first big invention was the idea of the bit. So the very idea that something can be in a state of 0 or 1 comes from this idea. This guy, I think I'm getting confused because there's an actor with a similar name. Oh yeah, so Michael Shannon is the actor, right? Claude Shannon is the inventor of information theory. So Claude Shannon, was the first person. Basically, his first question he asked was, what is information? How do you make a concrete, science of information? And so the basic idea he came up with was, okay, well, the simplest form of information is something is either true or it's not. And we can represent that with a bit. So a bit can represent a specific piece of information, and it's either on or it's off. And that is an objective way of thinking about information. So if you keep going down that path, eventually you come up with this idea of an algorithm. And an algorithm is like a set of steps that you do in sequence, top to bottom. And you might have loops or conditionals, but the idea is you're going to go top to bottom, maybe looping, maybe doing specific branches for conditionals. But it's going to take some input, and then eventually it's going to be done running, and you're going to get some output. And that's the essence of what an algorithm is. So same with the bit, and trying to say, like, how is this objective? How can you be objective about an algorithm? Complexity analysis aims to answer the question, can you measure an algorithm in the way scientists measure things, and how? So the basic way to think about this first is, like, if I were to ask you how, I could call on random people, I don't know how you feel about that, but Dave, how would someone, let's say you had no idea about Big O or complexity analysis. If someone said, prove to me your function is good or better than someone else's, how might you want to measure your program against someone else's? What might be a reasonable metric?
Give it the same input and see how long it takes to get an output.
Yeah, exactly. Yeah. So that's the most basic thing we think about in terms of measuring an algorithm is time. There's other factors, but how long it takes matters. And then, as Dave mentioned, you care about the inputs. Let's say you were comparing two algorithms that, supposedly both did binary search. If you were trying to compare my binary search to someone else's, we would use an input of the same size. And doing that, we might call a benchmark. So in that case, we're measuring performance. We're measuring how long did it take. And if I were doing that, like if I have over here, I have, I'm importing time, so I can do this little time counter here, and then I call measure function, which just runs the function, keeps track of the time and then prints out the output. So like in this case, I could say, okay, well, how long does it take to do something of how long does it take to run this increment list function, which I don't know if you guys have seen this before, list comprehensions and type signatures, but it's not all that important. The idea is just that I just want to start introducing you guys to more modern syntax or whatever, but basically we're going to take a list, and then for each element in the list, we're going to create a new list with that element plus one. But yeah, so if I run this function, which a function is a program, I can try running it with, with basically a list of 10 elements, a list of 100 elements, a list of 1,000 elements, and I can kind of see how it grows. And even if I'm not comparing it against someone else's, I can see, I could just see how it grows over time. So if I run this, I'll see like, okay, my first increment list with, like, basically each time I'm seeing one of these, the input size is doubling, and I see how, okay, the first time I double the input size, it went up by like a factor of 2. And then interestingly enough, when I double the input size again, it went up by like a factor of almost 10. And then again, more than 10, which is interesting. It's not clear why we're having that kind of performance thing. But the basic idea is that we have a function, and we see how the function's performance changes in relationship to the input size. So without worrying about what's in the input, it makes sense that if the input size is larger, sorry, if the input size is larger, of course, it's going to take longer to run. But the question is, how much longer? Because, for instance, if I had this might seem trivial, but if I had a function like define add 1, and it takes a number n, maybe I would make that explicit. It's going to take an int, and it's going to return an int. Is it not like int? Oh, it's lowercase. So it's going to take an integer and return an integer, and we're simply going to return n plus 1. And then I'm going to run this same thing, where maybe right below these, I'll do a. Does that just get me a new line automatically? Okay. So I'm going to call add 1, and just gonna replace these numbers. Hopefully you see where I'm going with this already, but if I run this, you'll notice that even though they took slightly different times, even when the input size grew, nothing changed with the add 1 function. And that kind of makes sense because we're taking in a number and we're just adding 1 to it. Our input size is growing, but the nature of our input and the function we're applying to it is that the size of the input doesn't really have an impact. And so complexity analysis in general is about measuring the impact of growth in input size to how your algorithm runs. Yeah, that is the core idea. And then the second thing is that right now we're measuring things in terms of how much time it takes, but how much time it takes is sort of like that's going to change as computers get better, right? So something that could have taken a very long time to run, 40 years ago can run pretty fast now. And the main difference is just that my computer is like 40 times faster or something, if not like 1,000 times faster. But Big O aims to measure an algorithm such that it doesn't care or know anything about your hardware or time. It basically just says, okay, starting from a list of length 0 up until a list of length infinity, what does that curve look like? So basically, as the input grows, do we have a pretty good situation where it's sort of like every time our input, doubles in size, we only pay, the the cost of one more operation, which is what, log n is? Or is it a situation where every time our input doubles, now the time it takes to complete is times 100, which would be like an n squared case. So we care about how, as the input grows, how much more effort do we have to put into running the program? And then the part where it gets mathematical and confusing is we care about what's called asymptotic behavior, which just means behavior as n approaches infinity. So as your list size, like we're not like even a list of size 10,000 doesn't really matter. We care about a list of size like so big we can't even imagine it, because that's going to tell us sort of the limits of how our program performs and just like whether this is even reasonable. Hopefully that makes sense. I think that is enough to start talking about the thing. But before I get into the lecture, does anyone want to talk in general? Just how do people feel about Big O? What are their preconceived concepts of it? How do they, like, I don't know. Yeah, I just want to get a sense of where people are at.
It's not in seconds, but rather in steps, which kind of hung me up first in the beginning a while ago when first learning Big O.
Yeah, exactly. Yeah, fair enough. I mean, it's not even in steps really. Part of the problem is it's just very abstract. You're saying it's just a measure of how. Yeah, it's hard. It's more a measure of steps than it is time. You are right about that. Oh yeah, before we go into the lecture, I'll just mention when we talk about complexity analysis, we generally care about two things. We've already mentioned time, which is essentially how long does this take to run? And then the complexity part is saying how long does this take to run as your input size grows towards infinity. The second question is how much new space does it need to run? And again, as your input size runs to infinity. So as you could see, like this function add one, I took in this input n, I returned n plus one. You could say, I mean, some people would count it, some people wouldn't, but basically in order to run this function, or when running this function, part of how this function works is that I do n plus one, and I'm not actually modifying n itself because you can't do that with integers in Python on purpose. Instead, I'm taking n as it exists, I'm adding one, and what I'm returning is a new value that lives somewhere in memory. So we would say that just like it is constant time complexity. So basically, no matter how big the input is, add one is still a single step, like a single instruction. Similarly with space complexity, no matter how big our input size is, we're only ever creating one new piece of data, and that number one isn't related to n. Compare that to a list. In a list, I'm starting with a list, and then I'm creating a brand new one to return it. So while this has time complexity of n, because I had to look at every element of the list in order to add one to it, it also has space complexity of n, because in order to do this function, I need to create new data that its size is going to be dependent on the input. So if I gave it a list of 1 million, its biggest problem would not be adding one to each one of those elements. Its biggest problem would be we don't have room for a data structure or for something that big on this computer. So on some level, time and space complexity are there to sort of make sure you're not doing something that your computer can't even handle. That said, you will see time complexity mentioned a lot more. Space complexity is sort of just this add-on thing that if you mention it in an interview or are explicitly asked, it's nice to know about. But people care a lot less about space complexity because if you look at the history of computers as physical things, space has gotten extremely cheap. You can easily buy a terabyte hard drive, and there's nothing about space complexity that cares if this is, like quick to access or slow to access memory. It's just, is there memory? So memory is very cheap, whereas people don't like waiting no matter what. So if you're if your algorithm takes a minute to run, that's going to be fine for some situations. But if you're trying to like train ChatGPT on your home computer, that algorithm requires either insane power that your home computer could never have, or it's going to take like weeks at least. And for most people, like basically the space complexity of an algorithm is going to affect whether it's useful or not useful in a situation way more, or sorry, the time complexity will affect that way more than the space complexity, because people don't generally want to wait for any operation on a website for more than like a minute. Whereas people generally don't, people have at least, 20 gigabytes sitting on their hard drive that is doing nothing. And that's a fair amount of space. Cool. But let's go through this lecture. And I'm going to try and do my best to leave a fair bit of time at the end, because this stuff is pretty academic in a certain way and most useful when you sort of get a feel for it. So like we said, big O is the complexity of your function in terms of input size. I would say this is a better definition of complexity analysis as a whole. We will get to the different types, but big O basically means worst case scenario. So that was something I should have mentioned when we were talking about those lists and stuff. Like imagine you have a search algorithm, right? And your search algorithm is just going to walk through every element one by one until it finds it. The big O of that is going to be, if it's not a binary search tree or something like that, the big O is going to be N, because you had to look at every element at least once. If your input size, if your array has length N, you have to look at N elements to guarantee you found or didn't find your thing. But then there's another thing called little o. No one ever talks about little o because little o means best case scenario. Best case scenario for an algorithm that is searching for a number in a list is boom, it finds it. It's the first number. Okay, great. So it's constant time best case scenario. But realistically, if you're searching for a unique value in a array of 1 billion elements, it's not going to be the first value. So little o is rarely cared about. Similarly, there's a big theta. Big theta represents average case. That sounds pretty useful. In practice, it's very hard to calculate average case. So people generally just care about big O, which is worst case, because it kind of puts a limit saying it can't be worse than this. This is our worst case scenario. Right, time and space complexity. Time, how much time does it take for the algorithm to run? Space complexity, how much working space or storage is needed. Note that your input never counts as storage you use. You get that for free. So here's an algorithm, and I guess we're gonna analyze it in terms of its O-ness right now. So just to know, this is a shorthand. Generally, you don't have numbers in the middle of that O, but we'll see why in a second. So this first one, we're saying for I in range 5, print hello there. So whenever you have a for loop, that's going to affect your big O, because instead of saying, oh, print hello there runs once, now we're saying, oh, well, it runs 5 times. So we're going to write that as O of 5 right now. And then similarly for item and array, well, we don't know how big that array is. So that's going to have big O of N, because it's going to be based on the array size N. And then we have this one here, big O of N, and then we're just going to print 3 things at the top level. That's big O of 3. And then the question is, well, what is the big O for the whole algorithm? So if you have something nested, you're usually multiplying that value. So if I had a for loop, like for item in array, and then within there had like, let's say item itself was an array, it was an array of arrays. So if I said for item in array, and then within there I said for array in item, and then print item, that would be big O N squared, because I'm saying for as big, or maybe technically big O N times M, because I'm saying that for as big as the array is, I care about how big the individual item in the array is. And then I'm going to be looping through each thing in the array. And for each thing in the array, I'm going to be looping through each item of it. But when you have things sequentially like this, you just add them together. So we would say, okay, well, this algorithm is O5, ON, ON, O3. Add those together, you're getting O8 plus O2N. And then that all collapses to big O of N. Why? So the first thing to note is that when you have a big equation of N's, you only care, I guess I'll just say it first in terms of the rules and then the why. So the rules are, you care about your biggest O term. So your thing that is, like if we had N squared here, that would supersede N. And we'll discuss that a little more later, but it's because N squared grows faster than N. And then similarly, this might seem counterintuitive, but if you had big O of 2N, we just call that O of N. We don't care about the constant in front of it. So why? The reason is because N, we care about N as it approaches infinity. So if you look at something like this, what does it matter, 5 or 3 or 8 compared to infinity? 5 and 3 and 8, they just fall off because infinity is not just a big number. It's bigger than any number. 5 and 3 and 8 might as well be 0 next to infinity. And then the second point is that what's the difference between infinity and 2 infinity? It's like, this might seem silly because then you could say, well, what's the difference between infinity and infinity squared? But the point is that 2 is such a small number that if you're multiplying 2 by infinity, you're really not changing it fundamentally. Whereas infinity squared, if you're multiplying infinity by infinity, that actually is now meaningful. So the only value that is meaningful in big O is essentially infinity, and infinity is represented by N. And so we care about things like N or N log N or N squared. We care about things that are that affect the nature of N, but we don't care so much about constants or numbers that aren't N, essentially. The exception would be something like 2 to the power of N, but that's still related to N. Hopefully that made some sense, but this stuff gets better as you see it. So here's an example of all the famous ones, essentially, and some sense of how, oh, right. So if N was 10, what would happen? So imagine you had an array and it had a length of 10. If you had some constant time operation, like something that just, printed the first element in the list or the 80th element in the list, or sorry, there's only 10. But the idea is this would only ever take one operation. And then binary search for something of size 10. I don't know that this is correct, is log of 10, 1. The idea is it's close enough. Log grows pretty slowly. So if we were doing binary search on something, a list of length 10, it would be near constant time. And then linear means we have to look at each element. So that's naturally going to be 10. Log linear is n times log n. Both log n and n times log n are a little odd because you generally won't make algorithms like this yourself, but log n is essentially the signature for binary search. It's the only algorithm that has that big O. And then n log n is the signature for good sorting algorithms. So I don't know that we ever get to those, but there's some not great sorting algorithms like bubble sort, that's sort of the classic. And then there's some good sorting algorithms like merge sort or quick sort. And the good sorting algorithms are good because they guarantee you it's going to take, instead of n squared to look through, like basically if you're trying to sort a list, one way you could do that is look at every element and compare it to every other element. And that's going to be n squared, but the guarantee of good sorting algorithms is always n log n. And then we have quadratic. Quadratic could just be seen as a for loop within a for loop. So for every element in the list, you look at every other element in the list. Then cubic, for every element in the list, you look at every other element of the list. And for each one of those, you look at every other element in the list. Hard to think of why you would want that, but if you've ever seen a triply nested loop, that's cubic. Exponential, again, I'm having trouble even thinking of what's a good example. But basically beyond n squared, people get wary of the big O because it's not going to grow well as n grows. And so by the time you hit 2n, people say, oh, that's not a thing. And then my favorite is n factorial. You will never see it in the wild, but it's almost like an exercise in how bad you can write an algorithm for the sake of complexity analysis. So the canonical example for factorial time is this thing called BOGO sort. So normally when you you could think of all sorts of ways you might want to sort a deck of cards. But one simple way is that you say, okay, well, I know I'm starting with ones. And let's say I'm going to do it in, let's say I don't care about the order of the faces. So you just say, okay, I'm starting with ones. So you look through the whole deck of cards. The first one you find, you put it down. Then you look through the whole deck of cards again from the beginning. The next one you find, you put it down. And you just keep doing that until you got all the cards in order. That would be n squared. That would be for every card. Basically, if your deck has 52 cards, you're going to look through perhaps all 52 cards 52 times, and then you're done. What is BOGO sort? BOGO sort is, let's say you had a deck of cards and you said, I want to shuffle this. So what you do is you throw it up into the air, and then you pick up all the cards and you look at them. If they're in the perfect order, you're done. If they're not, you do it again. You throw it up into the air and you pick them up. So basically you just randomly shuffle and then see if it's in order, then randomly shuffle to see if it's in order. This is provably the worst way to do that, in that it creates this situation of n factorial. Basically, you're relying on pure, basically you're relying on pure probability. And as you see, it grows terribly, where even for something of size 10, suddenly we have 3 million operations. And then normally we kind of do it like with doubling the input size, with increasing the input size by an order of magnitude, so like 10 to 100. But if we just double it, we'll see like, okay, well, 1 to 1, obviously that was great, and then 1 to almost 2, and then 10 to 20. And then as you see here, like this is sort of the core point of Big O, that like at quadratic, you can be like, oh man, it's 4 times, we doubled the input, but now it takes 4 times as long to run. Not great. We double the input, but now it takes 8 times as long to run. Okay, also still not great, but once you're in a situation of we double the input, it takes 1,000 times longer to run, or we double the input, it takes a number you can't even conceive of long. Like this is probably longer than the number of seconds in the universe. And that's just for an input of size 20. So it's a really good limiting factor of saying like, this is great, we love this. This is pretty good. It'd be nice to do better, but it's fine. This is impractical to the point that the universe will end before we finish running that. And it's actually not a bad feature in that you might say, well, why even care about factorial time? There's actually a good reason, because when it comes to cryptography stuff, cryptography usually works in such a way that if you have the key, or you are otherwise supposed to have access, you have some constant time or linear time way of proving that you are the correct person. If you don't have the key, you're in a factorial time situation. So yes, you could crack it with enough time and energy and effort, but it's designed specifically so that if you don't have the key, you're forced into this sort of exploding probability case where it's just, you're going to have to check so many situations that it's not going to be worth your time unless you're trying to hack like the president. And even then, if the encryption is good enough, we're talking about 1,000 years, best case scenario. It's not practical for almost anybody. Okay, so this number down here clearly can't be right if n equals 100 means to the power of 157. But either way, you could see how some things grow okay, some things grow less than okay. Right, and this is what it means approximately. And then this is the big graph. This graph is the entire idea. This lecture, I feel like the most valuable thing you could do in this lecture is just stare at this for a while, because it tells you everything you need to know, which is that there's this, I would say the yellow and down class is stuff, or honestly, even the orange and down class is great. Orange and down, I don't agree with this horrible bad fair thing. orange and down is excellent. Because it probably means you're doing as good as you can do, given that what that algorithm is. Then I would say ON squared is fair. People accept ON squared because you have to. Sometimes ON squared, ON cubed, even if you had ON to the 7th, it's not great. Obviously, it's going to run slowly. It's going to need a lot of resources, but maybe there's a legit reason you have to do that. Once you're at O to the N, you could see it grows in such a way that, like, you know, what input size do you want to use this for? Like, so some of these things grow great forever. Whereas, like, if you had ON squared, okay, well, let's say like this could be reasonable given your input size, but there's almost no input size where you're going to want something that so quickly becomes terrible. And ON factorial is almost like a straight line, perpendicular compared to the others. You never actually see it. But yeah, this image is worth sticking on for a second if we want to. So does this image make sense? Does it make sense how the x-axis represents the number of elements as it approaches infinity? Okay, fair enough. So these are just, I don't know why this slide exists. These are just some weird big O's. You generally won't ever think about, or I mean, maybe n cubed you'll see, or log n, but big O, as it turns out, is actual math, in that if you study this as an academic, you can be very precise in what you mean, and that's how you actually calculate new ones. But boot camps and even most academic programs don't teach you how to do it as real math because it's almost too complex. Instead, you're taught a kind of intuition, as in how do you intuit the basic way, or just the basic ways that you would measure existing algorithms. And a big way you do that is either, as we'll see, like if you have, nesting in a loop, you can, that goes from n to n squared. But then also it's just about knowing your algorithm. So if you know that binary search is log n times, then if you have to do binary search for every element in an array, let's say, then you have n log n. Okay, I've never seen that Venn diagram thing, but these are the other types of complexity analysis that aren't big O. Big O is the upper bound. It's the worst case scenario. That's what you care about. I was confused about it. I guess big omega is best case scenario. Big theta is average case scenario. Maybe not even exactly that. Little o is upper bound, excluding the exact bound. The point is, you will never hear, like, even if you got a PhD, you would probably never hear someone talk about omega, theta, or little o unless you were literally getting a PhD in complexity analysis. Okay, so now we're going to see some examples. Let me just check what time it is. I want to make sure we don't I give you guys reasonable breaks and stuff. Okay, we're doing okay. Yeah, so does anyone want to walk through for me why, like, how do you think the big O of this is being evaluated? Yeah. I'm just
looking at the array at memory location 0 and memory location 1. It knows where it is instantly, so it doesn't have to go through anything. So it says constant time.
Yeah. So the way I would say it is, or think about it, is like, okay, so this first argument value equals something. So this whole value thing is one step. And let's say value had to do something where it walked through an entire array. Okay, that's going to be, linear time, big O of n. But we looked at one thing. We would call that O of 1. We look at a second thing. Okay, it's O of 2. Maybe we're going to say, okay, well, we printed it. That's an operation 2. So we're going to say, okay, O of 3. But that all collapses to just O of 1, because if that array was, just had 2 elements in it, it's going to take 3 steps or 2 steps, whatever. If that array had 1 billion elements in it, it's still going to take 2 or 3 steps. So that's the essence of constant time, the idea that it doesn't care about the input. It works the same either way. And so if you made a function that, takes in a list, but just grabs the first element, that's always going to take constant time. Okay, big O log n. This is binary search. I said it to some people yesterday, I think in the stand down, but a lot of people left. But honestly, in my opinion, for the tech interview, the biggest single bit of information you can get for the tech interview is that if they give you some problem and you solve it, and then afterwards you're having this complexity analysis talk, they might say like, okay, well, can you analyze your program? And you might say, oh yeah, well, I see that based on how I did it, it's big O of n. And if they say to you, well, do you think there's any way you could do better than big O of n? The answer is binary search, because there's only one thing between constant time and O of n, and that's log n. And as far as I know, the only algorithm that guarantees you a log n result is binary search. So if you're being asked for log n, or if you're being asked for better than constant, but better than linear, but not as good as constant, because constant's usually obvious. They're asking you to do basically to rely on the fact that the data is sorted in some way, so that your algorithm can ignore whole swaths of the data, every time it makes a decision. So just to clarify, we remember that binary search. Oh, right here, we have an example of it. So we can see why binary search is log n. Or first we can just see that, okay, well, it runs better because this thing is going to keep going. Depending on what it's looking for, in this case, it took 11 steps, but it could have taken the whole 16 steps, which is n. And the question is, why is this log n? It's because if we had an algorithm that said, okay, well, somehow we know it's not on the first 3 elements, but it could be anywhere else, that would still be big O of n, because while we eliminated part of the data, it had nothing to do with the size of the data. It was just, okay, we're always eliminating 3 elements. So if we have an array of size 10, okay, now we only have to look at 7 elements. Maybe that's a big speed gain or whatever. But if you have an array of size 1 billion, only getting to skip 3 is almost meaningless in terms of your total performance. The reason why binary search is log n is because the amount of things you have to look at is going to grow based on this n, but it's going to grow at this very slow log n rate. Log n basically meaning as the input doubles, you only have to add a single new step. So I guess 2 to the power of 4 is 16. And the implication is that this approach can take no more than 4 steps. And if we were to double the input size, it would take no more than 5 steps. Whereas this approach down here will take no more than 16 steps. And if we double the input size, it would take no more than 32 steps, as in we have to look at everything at least once. All right. So I'm not positive why this slide is here, but I think it's here to demonstrate how performance and complexity analysis are kind of 2 different ideas. So it's definitely possible that you could have a scenario in which binary search, because it halves things in the way it does, and it always looks at the middle, it's actually going to take the maximum number of steps to look at if you're looking for the first or last element, as it turns out. So if we were looking for 1, we'd have to first look at the middle, which is 8, then look at the middle, which is 3, then look at the new middle, which is 1, then look at the new middle, which is the 0th index, and now we're good. Whereas if you're doing sequential search, maybe that's the first thing you see. So a sequential search could be faster than a binary search in practice, but its complexity analysis is still worse. So this is an important distinction between performance, which is kind of a real world concept, and you measure that in time, versus complexity analysis, which is a more abstract representation of how good or bad the algorithm is. But it's abstract enough that it might not capture the truth almost, in that it cares about inputs when they get really, really large. And for instance, it doesn't care about constants. But very often in reality, you do. Whereas if you had one algorithm and it was, if you had 2 algorithms and they were big O, but it turns out one was just one was big O of n, the other was big O of 2n. They're both big O of n compared as complexity analysis cares, but it is meaningful if one way of doing it takes half the time consistently compared to the other way. So my take on this slide is just we're making a distinction between performance as a real world concept and complexity analysis as an abstraction of performance. Okay, linear. Does anyone want to tell me why this is a linear function?
It's a loop.
You're checking every number in the array.
Exactly, yeah. So linear is going to be your sort of average case for complexity, where often you don't even pay attention, or sorry, you generally think about complexity when it comes to arrays or maps or something else where it has stuff in it, because that's the thing that's going to grow or shrink generally. And when you're working with an array, chances are you're going to have to, like, whatever you're doing with it, you're going to have to look at each element once. So linear time is sort of standard. It's how you accomplish working with an array that doesn't have any sort of special properties. You have to look at everything once. So anything you're trying to do to each element of an array, or anything that depends on seeing each element of an array even once, means at the very least linear. And something that can be obvious in that, like, can you imagine a sorting algorithm? Even if you don't know sorting algorithms, just the idea of sorting something, can you imagine a sorting algorithm that does better than ON time? As in, what kind of sorting algorithm doesn't require you to look at each element you're sorting at least once? As it turns out, no sorting algorithm is that good that you can look at each element just once. You have to look at least some elements twice, as it turns out. But it makes no sense that you could look at just half a list and somehow sort it, because you haven't seen that other data. So that's always a good way to think about, like, your lower bound on a big O thing. Lower bound meaning, like, you can't do better than this. So if your algorithm, if it makes no sense for the problem you're trying to solve that you don't look at everything at least once, you know you're dealing with best case scenario, big O of n. It might be way worse, but at least you know, like, we're not shooting for better than that, because that's probably not possible. Okay, so time and space complexity here. So we will see it. Let's just look at it. But does anyone want to justify these two cases? So why is the time and space complex? Why is the time complexity O of n here and the space complexity constant?
Because they're just single loops. So even though the O of n2, it would still just be O of n for time. And space, you're only storing two variables. So that number is never increasing. You're just adjusting their value.
Yeah, exactly. Perfect. Right, exactly. So we have these two loops. Each one would be big O of n, and we can't avoid the fact that if we're trying to sum or count an entire array, we got to look at each element. And so each one of those is O of n, and technically we could add them together, and that's O of 2n, but we drop the 2 because it doesn't significantly change how we think of the runtime. And then in terms of space, we do have two new pieces of data that we've created, but it's just two. No matter how big array is, that's not going to suddenly be 200 or 2,000 pieces of new data. It's just two. And so that 2 becomes a 1. Okay, examples of n log n, quasi-linear. I've never heard that term. Cool. I'm curious myself. Why? So does anyone want to analyze why this is n log n? I mean, it feels like a contrived example.
I think it's still cutting it in half, right? But still doing a binary search in the end, even though it is looping and appending thing.
Well, this is that like, if it's nested, you end up multiplying it as opposed to adding the big O's. So like we could say, for example, R equals new array that has a time and space complexity of constant. You are creating something new, you are running a command, but it only ever takes one command in one spot of data. Then we're in this for value in array. So we're saying whatever we're about to do, we're going to do it for each value in the array. So we're already doing something n times. And then what are we doing n times? I mean, we didn't even have to write this r.append. For n times, we're running binary search. So because binary search is log n, we're running a log n operation n times, so that the whole thing ends up being n log n. So hopefully that makes sense, because generally when you're going to be analyzing an algorithm after an interview, and I will say, I know it's annoying that like we often talk about like, oh, well, the interview's like this, the job's like this. For better or worse, it is that way. And you will never hear anyone, or it's extremely rare that big O will come up in professional software development, because you probably care more about raw performance where you're just measuring it in time. And it's sort of like if you got to the point that you're like on the React core team and you're making certain decisions like this, big O stuff is sort of tattooed on your heart to the point that you're not going to do things in an insane, naive way, or you'll find out pretty quickly. But the average programmer is never talking in big O. It's really just about having this common language for engineers to talk with each other about what is versus isn't a good solution in a way that's totally objective. Okay, time and space complexity here. Is this the same thing? So let's see, we're doing binary search once, and then for every number in the array, we're appending number plus value. So what's the big O here?
It should be the same thing, because the constant O of 1 is the best case scenario or a different case, but the overall algorithm is O n log of n.
You're saying the overall algorithm is big O of n?
I disagree.
And log of n.
Okay, why do you
It's the
just
same.
sorry, you can finish, and or whoever wanted to
No,
just
okay. Well, it's the same scenario as before, except for you took that binary search out, which is O of 1. But overall, yeah, the worst case scenario, you're always going to be O n log of n, because the looping through every number in the array and then the step to append it to the array.
yeah. Why did someone say they disagreed?
So I'm thinking that the binary search happens. Well, I didn't think about the binary search happen. Well, it happens for one value, right? Value is set once.
Mhm.
And then so wouldn't it just simplify, because this would just be log of n plus n.
Mhm.
So it would just simplify to log of n, wouldn't it? Because or
And-
no, it would simplify to n because n is worse than log of n.
Yeah, well, as far as I'm concerned, I'm pretty sure you're right in that.
Okay.
I don't know why this says n log n here. We'll see what it says on the side here, or it doesn't even say. But right, exactly. These are different. As in this case, I'm saying for each value in array. So for n times, I'm going to be running binary search. So I'm going to do something that takes log n times. So that's log n times n. In this case, I'm doing something that takes log n times. I'm doing it once and then getting a value. And then I'm doing plus something n times. N times, I'm adding a value, two values together and putting it in an array. But I'm not doing something log n times. I'm doing something log n, and then after doing something n times. So because that's not a times, but a plus situation, instead of having n log n, rather n supersedes log n because it's a worse runtime. And so this whole thing has a big O of n. Yeah, sorry about the incorrectness of that image. I think they just
So I have a quick question about that.
Yeah.
So the algorithm for no, like I'm just saying for here, the for loop itself, right? So for number and array. So every single number needs to be assessed. So that's already, we know, O of n, right? But then the next step, which is r dot append, is taking that number, appending it to the array. So why would that come down to O of n? I'm just a little confused on that, because it's technically, we're doing the same thing as before. It's just instead of doing the binary search and passing that as an argument, you know, I understand maybe if the space is a little bit different, but
It's because append itself, O1.
So,
well,
go ahead.
that depends on if it's sorted or not, right?
No, because append is always going to add to the end of the list, so you don't need to re-index everything else.
I mean, this is a good point to get into, which is, I guess there is a point here in that you are right for number in array. We're already going to walk through the whole array. The question is, what are we doing in the array? So if we're appending, like has been said, that we're just adding something to the end of the array, and we know that to be a constant time operation. But let's say we were doing something that wasn't constant time, and part of the problem is that because you or I didn't write append, we don't really necessarily know the time complexity of it without like looking it up. So let's say we tried to add to the front of the list. Does anyone remember what that's called in Python? Shift or something, whatever.
There's not a built-in function
you
for
could-
that in Python.
Yeah.
Okay, fair enough.
Insert.
You just,
Okay.
yeah, you just have to insert it.
So let's say we insert it at the front of the list or even in the middle of the list. The idea is in order to insert in a list, assuming a naive approach, what it's going to do is take everything else on the list and one by one shift it over and then put your thing in that new open spot. And because everything to the right you might have to push over, like let's say you were inserting at the first place, well, then you have to push over the whole array. So if you were putting something in the front, then I would say, okay, we're saying for number in array, so that's, you know, going to be big O of n already because we're doing something n times. But the thing we're doing n times is itself an a big O of n operation, because putting something in the front of the list means that if the list has size 1,000,000, you might have to move over 1,000,000 elements, which is 1,000,000 more instructions. So in that case, it would be n squared. The only reason this is just n is because r.append is a constant time operation. Yeah, it is the kind of thing where you just sort of have to get a feel for it over time. And you kind of only do that by not just like doing those leak code problems, but afterwards, like looking at their explanation of it, because it's sort of like every kind of like important algorithm or data structure is important predominantly because of its big O guarantees. So an array is generally only interesting because you can add, like, at least in Python, let's say, an array gives you this thing where you can append as a constant time operation. With a linked list, adding to the end is generally a linear time operation. And so that's a reason to choose one over the other. Usually every data structure has these like trade-offs in that way where, you know, certain things like, you know, maybe retrieving is going to be really quick, but like deleting is not going to be as quick. And so we'll see a little chart later, which it's a little overwhelming, the chart, but it sort of gives you the common big O qualities of like a given data structure's methods. Okay, what do we have here? Right, okay, this is the same one as here, right? We're saying time of O of n, that is true, and then space of O of n. Why space of O of n? Because we're ultimately creating this, you know, we are creating value. That would be big O of one, but this R, this new R is going to ultimately have the a size that is the same as our input array. So it's big O of n, because if array is size n, R is a new thing of size n.
Does
So I got
the length there affect it at all? Printing the length of R?
Yeah, so I would say in this case, I'm going to assume len is a constant time operation, because chances are an array is like, if the array was stupid, you would have to walk through each element.
I looked this up yesterday. So the length method is actually for all of the iterable data types in Python. They have like a self.length counter. And so every time they get added or subtracted, that just counts. And so you're only returning a variable. You're never actually iterating through to get the length.
Yeah, exactly. So even if your array of R was length like 1,000,000, it, because of how the array is designed, it has this internal quality called size, and it's just referencing that. It's not actually walking through it one by one and counting it. So length is constant time, and then we would say print is also constant time. Generally, yeah, I would say also in general, like it's okay to skip, like if a line has print in it, we don't really care. We're sort of saying, what about the core thing? Sort of, I don't know. I mean, it's a good point that if to do complexity analysis, right, you want to understand what everything in the code does, and you might not because you didn't write all of it.
Right, which my point here is questioning. I think it's just a weird example because you're unsorting it, right? Because your binary search has to be sorted, but then when you append to the end, you just unsorted your array. So it's just the example, I think, that's kind of confusing, right?
Yeah, no, I would agree with you. Some of these examples are contrived, and that doesn't help necessarily, as in there's no reason anyone would write code like this, because like you said, what's it for? Well, what's the point? And we're using it as a way to say, like, just, give me the time complexity and the space complexity on that, which is a skill in itself. But yeah, like what the code is actually doing is pretty meaningless here. And that's something that we could fix.
So it should be like trick question up top, right? Like,
or just we can have a little thing up top.
It's not trick question, but yeah, it just takes a little bit deep understanding, which is nice.
Yeah,
like if maybe we looked at this a little bit later, we'd be like, oh yeah, dude, that sums down to O then. But right now, it's definitely tricky.
The point being that you can do you can do space, you can do complexity analysis on anything, including code that is relatively meaningless. As in, I have no idea why someone wants to accomplish this, but the fact that they are doing it means I can tell you it's big O for time and space. So do you see how that's useful? That like it's almost like
that's good to think of that way.
Yeah, like you might like someone
like it was probably intentionally written this way.
Yeah, maybe.
I
mean, I think there's a certain amount of churn with curriculum where one instructor changes something and then the next instructor just notices it and might say like, oh well, I would have done it a little different. But whether it was on purpose or not, that is it's almost like an SAT question. It's just like, can you arbitrarily tell me the answer to this like contrived thing that's going to prove whether you know how to do this thing or not. Here's an example of n log n. You've not learned about merge sort, but merge sort is pretty cool. And this picture is nice for giving you just a general sense. Merge sort is one of the major sorting algorithms. So the way it works is we take a big list to start with, and then the first thing we do is we break it up. We break it up until, we break it in half, and then we break those in half until we have lists of length 2 each. And then when we have lists of length 2, we just compare the 2 elements, or if there's one, we don't compare it at all. And we compare the 2, and then just whichever one's smaller gets the first spot, whichever one's bigger gets the second spot. And then we do that again with lists of length 2, where we say, well, because now that it's sorted, we can compare these 2 by saying, well, which one's smaller, the first or the first from the first or the first from the second? And we say, okay, 3 is smaller than 27. Cool. We put down a 3, and then we say, what's smaller, 27 or 43? And then we say, well, 27. And then we say, what's smaller, 38 or 43? 38, 43. And at the end of it, you get a sorted list. And it might not be immediately obvious why this is better than n squared, why this is better than looking at each element twice, or looking at each element once for each other element, rather. But as you can probably tell just intuitively, we're getting that log n from something binary search-like, where once we have 2 things that are sorted, we don't have to make as many comparisons as if those two things for unsorted. So imagine if I had like, if I was comparing, basically, if I didn't know the order of these things, I'd have to say, is 27 smaller than 3? Or I'd have to say, is 27 smaller than 38 or 3 or 43? But because of the way it is, I can just say, is 27 smaller than 3? Because I already know it's smaller than 38. And I already know that 3 is smaller than 43. So this is the first comparison. And based on what I do here, then I can compare this to the next one. And then I can say, okay, it's still smaller. That's the new one. And then I compare this one to the bigger one. And it might not be obvious why it is big O n log n, but it's getting us a slight speed up from normal sorting stuff because we're doing this sort of sorting branching strategy where we can collapse things at each step. Hopefully that's an okay explanation. But it's a little hard if you haven't seen merge sorting. We never actually get into teaching sorting algorithms, which the average person is not writing a sorting algorithm, but they are a great way of seeing big O in action. Okay, quadratic time. Can anyone tell me why they think this is quadratic?
Nested for loops.
Yeah, right there. That's always going to be your answer. I mean, if you did something in here that was also expensive, it would be more than n squared. But if you have nested for loops, you're saying I'm walking through this array once, and for each element, I'm walking through the array an entire time. And so that's going to be, you know, n squared, because if you had 100 elements, now you're walking through it 100 times, and for each one of those elements 100 times, so 100 squared, 1,000, same deal. That's quadratic time. Okay, what would the space complexity be? Just using the tools we have, isn't the only tools we have so far really are, unless we recognize something as like binary search, it's either a single operation or it's linear time because we're walking through an array, or because it's nested, we're going to be, you know, walking through an array and then doing something, or walking through an array and walking through an array and then doing something. And then in terms
Is
of,
it? Oh, sorry. Is it O1?
let me see. So we have this new array. I would call creating the new array O of 1. And then for each number, we're walking through it. And for each thing we walk through it again. So we're going to be performing this operation n squared times. And we're just adding a number to R, but the end result is that R is going to have, you know, one element for each time this walks through. And this is going to walk through one time for each time this walks through. So I'm pretty sure our space complexity will also be n squared. And we don't have an answer, but I think this is, yeah. But yeah, I believe this would be n squared space too, because let's say array had size 100. How big is R going to be? Or let's say array at size 10, how big do we expect R to be? Well, for each one of those numbers 0 to 9, let's say, we're going to walk through each one again. So that's going to be, we're going to perform this 100 times, and we're going to add 100 elements to R, even though array was only size 10. All right, well, just moving on because we want to just see these. Even though you just saw that, very similar problem. What do we think the time and space complexity should be here? So we're walking through an array once, and then for each time we walk through it again. And for each, yeah, I don't think I'm explaining nesting well, but for each element in the array, we look at each element in the array again. And for each one of those times, we also look at it again. And then we do something at each stop, which is append.
Isn't this one cubic?
Yep, both time and space would be cubic, yeah. And I mean, you've probably discovered it by now, but if you're doing big O in a casual colloquial way like we are doing, your number one sign is nesting, for loops. For loops inside of each other make the time and space complexity grow. Yeah, that's going to be your biggest like cost. And because of the way complexity analysis works, you can kind of instantly in your mind just ignore the print statement, ignore the R. You know your cost is coming from this nesting. The further the nesting, the greater the cost generally. Yep. Okay. So examples of O2 to the n. So this is a good example. Remember the Fibonacci function? Or maybe, I think we've discussed it to some extent. So Fibonacci could be.
Boy, do I.
What was that?
Boy, do I.
Oh yeah, yeah. Well, Fibonacci ends up being pretty interesting because it runs us into a problem and then there's a solution to that problem, which we aren't getting to here. We're just sort of using complexity analysis to see the problem clearly. But yeah, so for Fibonacci, if n is less than or equal to 0, or I guess I'll ignore that one, we print incorrect. If n is 1, we return 0. If n is 2, we return 1. Otherwise, we return Fibonacci n minus 1 plus Fibonacci n minus 2. So let's say we had Fib 5, right? You'll see here, well, Fib 5 creates Fib 4 and Fib 3, which, you know, you see we're doing the same thing a lot. Like, in order to do Fib 4, we have to know Fib 3. In order to do Fib 3, we have to know Fib 2. In order to do that, we need to know 1 and 0. And we end up just doing 1 and 0 over and over and over again. So we're doing a lot of unnecessary or seemingly unnecessary recomputing of the same values. And the way, because of the way this grows, so like when something is log n, it's because it's sort of taking advantage of a tree-like structure to eliminate half the tree every time. When something is O to the 2n, it's the opposite, because 2 to the n is the opposite of log n, or log base 2n. And it's that instead of using the fact that your thing is structured in a tree-like way to eliminate half the input at a time, instead computing your thing explodes into a tree. So every time you run Fib 5, you have to run Fib 4 and Fib 3, which themselves have 2 children, and that creates an expensive operation. So this is probably the most complicated odd one we've seen to date. How do people feel about this one? Maybe someone has a sense of how they might fix it.
I thought I ran into this where you had like, I think Josh did something with caching, right? Where you say, I've done this one, Fib 1, and I've done this Fib 0. I should remember what that is, and then not have to ever do that again.
Memoization.
Yeah, memoization.
Memoization. That was the word.
Yes, that's the word you're looking for. So exactly right. So this is this is a good example of how like Big O is about your approach. It's not fundamental to the problem. So this way of doing it, this naive way of doing Fibonacci, ends up being Big O of 2 to the n, which is really bad. And yet someone can look at this and say, wait, if I'm computing 1 and 0 over and over again, what if I just flip the script? And if I'm being asked to compute Fibonacci 5, I know I'm going to need those previous values. So I'll just compute 0, then compute 1, or 0 and 1 are actually given for free. But then compute 2 based on 0 and 1, and only do it once. Then compute 3 based on 2 and 1. Then do 4 based on 3 and 2. Then 5 based on 4 and 3. And so if you do it that way, you're only computing fib for as many elements as your input size, which in this case would be that 5 or n. So we can take something from being O2 to the n to being O to the n just by doing it in a smarter way. So, and all we have to do is sort of flip the script and say, why are we drilling down when we can sort of build up? So yeah, that's, I'm happy people have heard of memoization, because that is the big idea there. And it's cool. It's cool that your time complexity, or just, I guess that's a good, the point there is that it's almost like time complexity is not opinionated, or just complexity analysis is not opinionated. It's a way of telling you whether your algorithm, it just tells you something about your algorithm. And if you see that the way you solved it, it works and it's a working program, that's the first step. But then if you analyze it and say, oh, wow, it's O2 to the n, you might say to yourself, is there a different way? Whereas if you got O of n right away, you would probably say, I think that's it. I don't think there's a way to do this that involves not looking at every fib value from 1 to 5. Whereas when you look at this way, you say, I think we're repeating work. There's probably a better way. Let's see. Example of O to the n factorial. If n is 0, print a bunch of asterisks, okay, and then I say for I in range n, function n minus 1. What? I don't. What? Oh, so if I had f of 5, then for 1, 2, 3, 4, or for 0, 1, 2, 3, 4, I would call f of 4. Okay, so I think what's happening here is like, if I have f of 5, then that means for 5 times, I'm going to do something 4 times. For 4 times, I'm going to do something 3 times. For 3 times, I'm going to do something 2 times. So basically, it's 5 times 4 times 3 times 2 times 1, which is what factorial is. In practice, if you honestly, I think it's an accomplishment if you manage to get something with a complexity of n factorial, because it's almost like failing the SATs. You need to know what you're doing to get a 0 on the SATs. Similarly, you're not going to stumble into an n factorial solution. It's almost like just proof that you understand complexity analysis because you've designed something perfectly wrong. You can't do worse. There's no, I'm pretty sure that's the limit of how poorly something can grow.
I'm gonna double nest the recursion.
Say that again.
I'm gonna double nest that recursion.
And
Don't
yet,
tell me you can't do it worse.
but I think that's the problem there, that basically, if you like n squared, like whatever that turns out to, n factorial times n factorial is not worse than just n factorial. N factorial is like, because the factorial supersedes the squared. So that's why you kind of can't do worse. Even if you like, obviously that would be worse performance wise, but this is the worst class of performance. Okay, here's an insane image. Just I think we have Zainab made a little program that we can run this stuff and see sort of time that it takes based on input sizes. But as we basically see, just getting some stuff out of the way so I can actually read it. Like with the O1 case, it's taking a second just about, no matter how big that input size gets. N log n, it doesn't seem much worse. I mean, yeah, I mean, it's interesting. Yeah, I would expect it to be a little worse, but it looks almost like it's linear. And then I'm getting, well, I guess this is just the reason why performance and complexity analysis isn't the same thing, because, you know, sometimes, you know, the fact that the computer can take just about the same amount of time to do orders of magnitude greater probably says more about how fast that computer is than anything about your algorithm. It's just that you're not seeing the difference in performance, or maybe there's an optimization happening somewhere that you're not responsible for.
It's probably taking that 1 second to initialize the thing.
As in to initialize the array,
Yeah.
that size. Yeah, there's a good point there. If this was tested correctly, the time doesn't include the initialization. But you are right that like the things that take time versus don't take time in a computer can be very different from this complexity analysis thing. So basically, if a computer has to run 1 million addition operations, no problem. It'll do that in a second. If a computer has to talk to the hard drive and say, we don't have enough memory in main memory, I need to store something to free up some space, and then I'll put you like, once the computer has to talk to a hard drive, it's a whole nother, things are going to take a lot longer. So right, performance often has more to do with how a computer actually works. And I don't know that you guys have ever heard this analogy, but I want to share it just because it helps understand what takes short time versus doesn't with a computer, and it also helps you understand how a computer works. So basically, imagine you're in a library. You are a person reading books in the library. You represent the CPU. You're the thing that actually reads things. And then you have a desk, and that desk can have maybe 20 books open on it simultaneously, right? So those 20 books represent, let's say, the CPU's registers. They're the memory it has immediate access to without doing anything. And then the rest of your library represents your memory, as in you can get up and go get another book, and maybe you only have space for 20 on your desk at a time, but you can easily get up, walk somewhere in the library, come back, and it might take, a few seconds, a minute, but you're going to have that book in not that long, and now you have it. So that's memory. Memory is the next level from the CPU's registers, which is sort of its internal memory. And then the next step after that is, so you're in your local library branch, right? And you can look at all the books, and that's your memory. But it turns out there's a much larger library with even more information, but it's on the moon. So your hard drive is, you got to get on a rocket ship, go to the moon, get the book you actually care about, and then come back. The minute that your computer has to talk to a hard drive, it's going to take an order of magnitude greater performance hit than anything it's able to do just locally dealing in memory. So that is always going to be your big performance hit. And in the real world, you care about things like that, what we would call like a cache miss or something. That means you're looking for something in memory. It's not in memory. So you got to go to your hard drive. That's a little off topic, but basically I just want to say how that's why these numbers probably are the way they are, that as you see, this one is not growing until suddenly it's 8 times worse. And I just, to me, these images illustrate more than anything just how usually there is this gap between complexity analysis and benchmarks and just, actual performance and time, because that benchmark cares more about like bottlenecks that have to do with like your physical computer or maybe your network. And that's another point that is related to complexity analysis. There's this saying in the world of software development and computer science in general, which goes, don't prematurely optimize. And what that means is you will often have situations where you say like, oh, this can be made slightly better. And so you start modifying something to make it slightly more efficient. And you might do that often. And then when your product finally is ready to come out, you realize, oh, well, all that optimization I did is meaningless, because the real bottleneck is the fact that we're talking over a network, and that, can involve seconds of downtime. And so it doesn't matter that I'm shaving off, 100 milliseconds when I run this operation. The great amount of waiting time is going to be that we're talking over a network. So in general, don't worry about optimization until, one, if you write it in such a way that you can't even run it locally and get any kind of result. But basically, don't worry about optimization until you run into a real problem and you see you can actually measure what the cause of that slowdown is. So complexity analysis is almost like, don't even take action, just note what the complexity of your function is, because it might matter when you down the line are trying to improve performance. Is this okay? A little bit more about benchmarking. Benchmarking is just measuring your algorithm using something like time. And that's it for that lecture. I see it's 9:30. We've gone for a little over an hour. We still have over another hour, I believe. So I'm going to give you guys a 15-minute break now. And when we get back, we will work through maybe some of Zainab's big O demo stuff, or otherwise just talk about this stuff, because it's one of those things where you just have to build up intuition, basically. It's not, the essential problem is that to teach it fully, thoroughly, is beyond what our course offers, and also what I don't remember how to do big O in a mathematical way, and most people never learn how to. It's just you build this intuition, and that intuition gets you 95% of the way there. So we'll do some more of that when we come back, but we'll come back in 15 minutes. Okay, and I'll stop sharing. I will pause. Okay, we should be good now. So hope everybody's back. See, I have some stuff on the screen. We have a fair amount of time left, so I'm honestly, I'm at something of a loss of how to teach this well. It's a tough topic. But first thing I want to do is just look through this the slot, or sorry, the lecture notes we actually have. And people mentioned, I think, that they were confused about space complexity, so we'll talk about that a bit more. All right, so these are just examples of, this is constant time because we're appending something to a list, and that just appends to the n, and that's a constant time operation. Linear time, we're going to walk through the whole list. So I guess we've already seen this to some extent. This is n squared because we're doubly nesting the for loops, then doing something inside. Okay, you've seen all of this. Okay, so something I think that we're going to do instead is there is a website here I'm looking at. I can share it in I could share it in the chat, I believe. So that's what I'm looking at right now. And this is some general like study guide for tech interviews. But the reason I want to do it is that we can look at individual data structures or topics and then see some complexity analysis associated with it. So if I click on an array, I can read a bit about an array. But this is the part I want to really point to, which is arrays have these different operations, and those operations have a big O. Oath, yeah. So if I were to open that here and this scratch pad over here, we could start doing that. As in, like, let's say I made my own array class, right? I'm gonna make a class, and I'm gonna call it array if that's not already taken by Python. I don't think it is, and I can make my own array, which I'm gonna say, like, maybe when I first create the array, we don't do anything, but maybe it doesn't take anything initially. Does init take self? It does, right? Yeah. But right, so we're just going to say, let's say we're just automatically giving it an internal representation. So I'll just write something like internal. And it's just going to be an empty array. And that's the whole of array right now. So if I were to say, like, my array equals array, and I can't give it anything to begin with. I have an array, and then I'm going to say array dot, and someone told me what's the way that I make it so you can't, yeah, like that, right? Yeah. So someone tried to access internal now. What happens? Doesn't like doing that. Okay, cool. So right, so now I have an array, and let's see what each one of these things would be. So let's say I want to insert, or not insert, let's say I want to append to the array, right? Well, how do I do that? We're going to assume I don't have anything. I can't do anything but sort of what's the word, index into this array. So in fact, I would want another thing, not just self dot underscore underscore internal, but it's going to be my responsibility to know how big this array is. So I'm going to say self dot size and make that equal to 0 initially. And the first thing someone might want to do is put something at the end of the array, right? So I'm going to call that append, just like our, real arrays append. It's going to take self, and it's going to take a value. And then in order to append something to this array, I know my size, which is going to tell me where the last element is, or the last, how about I'll have another internal thing where I'll keep track of the size like this, but I might also not just care about the size, but care about self dot last index. I'll say there's a last index, and that last index holds where I should append a new thing. And in this case, it will be, I think I'll say -1 because every time I append something, I'm gonna want to find out the last index and add 1 to it, and then that's where I should put the thing. I think that makes sense to me. So when I append something, I'm gonna say self dot last index plus equals 1. And then I'll say self dot internal at that last index equals the new value. And then what does Python's array do? Like if I were to say 1 dot append 2, am I not doing that right? Okay, so it doesn't return anything. So we're not going to return anything either. Well, that might be the next thing that we would want to have something like def get array. Okay, so I have my array, and I'm going to say my array dot append takes a value, and maybe I'll add a 2 to it.
Don't forget to iterate self.size when you append.
Don't forget to iterate what?
Self.size when you append something.
Good point. Yeah.
And think really for your append, your self.internal at index could just be self.size instead of
Say that one more time. Your self dot.
on line 9.
Uh-huh.
If you're, why don't you just add it at self.size?
Yeah, I was wondering that whether they would be the same thing. So I think you might be right that I could just do it at self.size, and then the next line is to update size.
Yeah.
Okay, well, let's just see if this works right now. List assignment index out of range. Why might that be? It's an empty list, and I'm trying to put something at self.size.
I think it's because index 0 doesn't exist.
Right, yeah. So part of this was I was trying to make it so we had a version of an array that's more like a real array and not using all the Python special stuff. So maybe I will give it an initial size or max size to begin with. So when I make an array, I might say it's an array of size 10. And then I would say something like self.internal. So my actual size for what's in the array will start at 0, but I'll say self.__internal equals I know there's a way to do this, something like a list out of range max size dot, is there like a fill? No, is there what is clear? Not sure.
I think clear just removes everything from it.
Right, but would it still be of size 10 then? Like if I said print self.internal comma length of self.internal, I wonder what would happen. I'm already getting confused. Object of
The clear took everything out, so it can't measure the length because there's nothing in it.
okay, so that's what clear does. Is there any way to just fill it with a number? Like, is there a way to fill it with zeros real easily? Python. Yep.
If you do what is it called? 0 for I in range.
Where would I write that exactly?
On line 4. So the internal, instead of list,
Uh-huh.
you can do 0 for I in range. I also put it
Zero I in
in
what?
range. Yeah, in range, and then just remove the yellow parentheses.
Yeah, and I wrap that in a, oh, okay, so a list comprehension.
Yeah.
Okay, cool. So I'm actually going to put that as none. That makes a little more sense to me. And now if we print it, right, we have a list full of none, and then it has size 10. And then once we print it, we'll see something like just that. Yeah. See, I kind of like that. I'm going to say, in fact, instead of doing that, we'll just have my array dot, or we'll print it. We'll just say print my array, and the nature of our print is going to be something more like we're going to just filter it where I'm going to say return the stringified version of what is it? It's filter, right? Filter takes a lambda. If you're not familiar with this stuff so far, it's okay. I'm just saying filter's first thing is the function and the next thing is the iterable, right? So the lambda followed by our internal. And basically we're going to return it as long as X is not null. This might seem like a pointless function, but I believe this works. Not quite. I filtered. Don't want to see this anymore. Why doesn't this work? Can anyone?
Well,
Maybe-
filter returns a list, right? So we have to do like
Oh, do I have to?
iterate through the list that it returns.
Well, is it that filter doesn't return a list, but rather a filter object? Yeah, that's the answer.
Or, yeah.
Okay. So basically, I went a little bit out of my way, but now we have it a way of saying we have arrays that only have, can only go up to the maximum size we say, and here's some operations on it, and I can print it. And I'm doing all this just so that I can talk about the big O for these things. So the first thing is append, right? I don't have full access to the Python stuff. I'm writing it myself. So what is the time and space complexity of this append operation? We're starting with the array and we're appending a new value to it. How long in time and space complexity, or how long in time complexity terms should append take?
Constant time.
Yeah, right. Because we already have this internal representation, we're able to index right into the spot we want and then set it. And then we do this one additional thing, but we're just doing one operation. And no matter how big our array is, even if our array was like this big, the append itself is still just one step, or a number of steps that is constant time. And then how about in terms of space complexity? So if we call append on a given array, how much new space do we need to create relative to the size of the array?
The n plus one.
Will that be linear?
Well, the question is how much new space are we creating? So let's say we have an array of size 10. By the time after we run append, what has changed?
It's also constant time.
Exactly. It's also constant time because only ever creating one new bit of data. In some, I mean, it's actually right. It could be confusing if we were like creating a new array. But actually, as it turns out, we're not even creating, it's constant time because we're not even creating a new thing. We're just putting something somewhere, but we're actually not creating, like we could say this has space complexity of linear because depending on that n, we're creating a new piece of data of size n. But append is not actually creating any new data. Okay, so we have append, and append would be equivalent to insert at the end here. And that takes that amount of time. And let's say access. So I could have, we'll just say, we'll have a function called index, where I could say def index self and index to find. And maybe I would do a check here to say something like, probably want to hold on to my max size to say something like, I would just make sure that that index to find, if index to find, I want to make sure that it, or if it's less than 0, or it's greater than, what is it, max size minus 1. If either of these situations are the case, then maybe I would want to say, I would just want to like throw, not throw, what do they call it in Python? It's raise index error. That sounds good to me. And if that's not the case, we'll simply return self dot internal at the index to find. So let's try that. Maybe I will print my array dot index of 0, 1. See that? Okay, great. So that seems to work as well. And if I gave that like a 4, I wonder, I think it will not complain because I'm only concerned with max size, and that was silly of me. I actually don't want that. I want to make sure that it's based on size. I don't know that I do want to be keeping track of max size. So if I run this now, I should get an index error, right? Yeah. Okay, so kind of going out of our way here, but like now we have access, right? And based on how we wrote access, what is our time and space complexity? It's fair, I'll just give it to you. It's also constant time. I mean, it's constant time for space because we're clearly not creating anything new. We're just grabbing something. But it's constant time for time too, because we're able to index an array instantly, which is just something we can accept about an array without knowing too much of it. We get index for free. But there's, more things here. So for instance, search, if it is already sorted, if I could somehow know that, we get this O log n guarantee, which is the binary search. And then something like insert or remove, which are similar concepts, are going to require me to shift over the whole array. So let's say I tried to create that insert function. Insert is going to take the array. Let's see what an actual Python array has. Like if I were to say array dot insert, I just want to see what the signature is. The index and then the object. Okay, so I'm going to give it an index, and then I'll give it a value to insert. And how would I do this? Well, first I would have to look at what is currently at that index. And I could say something like self dot index at the index. Hopefully that's not so confusing, but these are different ideas, the method and the parameter. So I want to get the index at there. I see it's going to give me this raise index area if that's the case. So I might want to put a try in there. And I'll have an accept. So if I'm able to put it, or if I'm able to grab something at the, or if I can grab something at that index and there's currently something there. If not, then it's out of bounds. In that case, I should try to just put it where they said to put it because there is room there. Oh, this is getting confusing fast. I mean, I could say something like self dot or I could put it at that index. Self.internal equals value, and then I would have to update the size, and the size would have to be equal to the index plus 1. So, and then what else am I missing here? Right, the pushing over, where let's say I do find that there is something there. So I could say something like old value equals that. And then I could say self.internal, the current index is equal to the new value. But now I got to push everything over, including that old value. So I need some kind of for loop where I say for I in range starting from this is getting probably more confusing than is helpful. So I almost want to give up on this because I think we're getting into the weeds a little too much. But how useful is it to see this sort of thing? To see that like Big O is usually not one off on like, oh, this is some specific algorithm, but rather for a data structure, you kind of get to learn, oh, well, access is constant time. Search is linear. Insert, is linear. And that is, those are all qualities of that algorithm, or sorry, of that data structure, so that you can compare it to another data structure where if now I say, like, let's say I'm going to try and look here, and instead of arrays, I want to look at linked lists. So the main reason you care about a linked list is that you can compare these things where you could say, okay, well, access in an array is constant. Access in a linked list is linear. And that makes sense because in an array, you can just jump to the element. A linked list, you have to walk through all of your elements to get to, the fourth one or the 1000th one or whatever. Search, okay, well, they're the same for search. Insert, well, insert can actually be constant time because I always know where the last place, the next place to insert is, and it's the opposite with an array. With an array, if I insert in the in the middle or something, I'm going to have to push everything off. And linked lists, we just wherever we want to put it, we put it down there, and then we stitch the two, what came before it and what comes after together. Same with remove. So the reason why Big O is useful is because let's say you had something like you were trying to make a database or something, and you knew that the nature of your database was that you were going to be accessing it constantly. And you were only every now and then going to be inserting a new piece of data. So if you were going to be accessing it constantly and only, from all over that database, and then you were only going to be sometimes adding new elements, well, in that case, an array seems like a good choice because array gives you a really good time for access, and insert's not as good, but we're not doing that as often, so we are less concerned with it. Whereas let's say you had a different sort of use case where you said, okay, well, we're adding to this database all the time. We're doing that over and over and over again. we're only actually looking to retrieve something from it every now and then. What we really care about is speed of insert. Then you would want to choose a linked list. And that's the main reason you choose one data structure over another, that you care about a certain operation that you're going to be doing a lot. And that data structure gives you a good cost for that operation. Yeah. So what else can we look at? I think we have like 45 minutes left. We'll probably give like 15 minutes of that back to you for a break. But given that we have another half an hour, I think maybe the most useful thing would just be to talk through questions and confusion, because this is a topic that is hard to grasp because it's not very practical up front. So right, let's just ask questions and write some code. How does that sound?
Woo.
All right. Well, besides the woo, are there any questions or just woos?
I have a question.
Great.
So to me, the hardest part of Big O is knowing what the complexity is of built-in or imported functions and methods.
Yeah.
And is there, aside from, you know, making assumptions of like this thing probably loops through something, so it's O(n) or whatever, is there a rule of thumb or any sort of trick to knowing that stuff other than just looking up every single thing that you use before you use it?
Yeah, so not exactly, as in there's not necessarily, you have no idea how the thing was implemented. If the thing you're talking about is like an array, and the idea is Python made the array and you don't have to do that, you can kind of expect that they're going to do arrays as best as they can, and you'll get the sort of guarantees you would get just by searching like time complexity array. But there's generally no way of knowing if you didn't write the code yourself. And yeah. Oh, I thought I heard something. There's not necessarily a way of knowing, and even using Python itself, Python is kind of a high enough level language that, for instance, like if you did, you know, array.append, you don't really know how it's accomplishing that. You don't really know how it even represents arrays in memory, because its arrays are a little more powerful than regular arrays. Like they can have anything in them, not just a specific type. So it's a little hard to know just by, yeah, like you don't know. You don't know. And the assumptions you do make are based on sort of the core idea. So the reason why someone can say that access time is constant in an array is because an array is normally represented in memory. And let's say we say that array starts at the value, you know, the memory value 0. And we'll say that we're storing integers there. So we have like an integer 4. That's what it like holds. So we'll say this is the memory address, and this is the value. So just to be as correct as we can, so this is just saying, you know, I have these 8 bits that represent a memory address, and in this case it's 0, and there's a 4 there. And then because the nature of an integer is that it's going to be like exactly, let's say we're representing it as 8 bits or something. Let's say, you know, this is an 8-bit integer. What that means is that at memory address 0, I put a 4, and then at memory address 8, I put, you know, a 6 or something, and at memory address 16, which let's just forget about hexadecimal for a while. Let's just say, okay, we're actually going to, I wish I could just, okay. we're actually going to represent this just as like the number 16 or something, assume it's that kind of system. So the reason why I can do access in constant time on an array is because I know how big an integer is, and I know that it only holds integers. So I can just jump to, you know, the 30th element by saying, okay, start with the original memory address, and then plus the size of an int, and multiply that by the index I want to go to, which is like 30. And that's going to give me, you know, the memory address for the 30th piece of data here. And if you were in a language like C, you'd have to be explicit like this. That's how you would get to that final index. But that's the only reason that access is constant time, because even if you didn't have access, a way of saying like array 30 equals 4, what you're really doing with array 30, if it's a real array and you're not assuming all the stuff Python gives you, is you're just doing a single calculation, which basically, you know, says starting point plus index times size of an individual piece of data, and this would be a constant time operation. We're just, you know, calculating a bunch of numbers. And so that would be constant time access. Again, maybe that is a tangent, but like the idea is that you don't know what a function you didn't write does, and you don't know what even a lot of built-in Python stuff does because you didn't write it. But there's always a way of, like, if you understand or see how that thing was written, you can analyze it. And all these guarantees come from the fact that a computer either can or can't do something in a quick way, where it either, you know, constant time means I can just jump to the answer, whereas linear time means I have to walk in order. So I hope that was helpful, but feedback, any other questions? Okay. Anyone wanted to talk about size complexity a little more, space complexity?
Yeah, I would, because several examples back, we were talking about size and or time and size of one of those examples. And basically it was an array and we were just appending to the array, but you're saying that that would have been O of n or something. And I thought it would be constant because all you're doing is like adding to that array that already exists.
Yeah, well, adding to the array would be constant time. Well, right. I mean, that's a good
Well, we're
point.
talking about size. So, yeah, time I get, but
It gets a little confusing because let's say we had a list and we're going to call it, you know, empty, and then we're going to say for I in range 100, and then we'll say for J in range, I'll just again 100. So for each one of these things, I'll be going through 100, and then I'll have, you know, I times J, and I'll say list dot append I times J, and then when I'm done with it, I will print the list. I would expect this to be a pretty long list, and it is a pretty long list. I don't particularly care about what's in there. Maybe I mostly just care about finding out its length. Okay, which makes sense. 100 times 100, right? That would be 10,000. But right, so the question is, what's actually happening here? Well, running list.append, if that array already exists and has space for it, that is constant time. And yet we're kind of accounting for the fact that in the background, we know that Python has to do this thing where if it has an empty array, maybe that has 10 spots in it initially. So in terms of the real array, it's sort of, you know, gonna be an array of size 10. And then once that's filled up, it's going to create an array of size, let's say 100, and refill those 10 in, and then keep going. And so by the end of it, we've created a fair amount of memory in order to create this list. And we'll say just at the least, if we're ending with an array of size 10,000, then we'll say that we created, our space complexity is, at worst, going to be relative to that 10,000.
So
But
would
you
it-
are
it'd be
right
fair
that
to
if,
say that would be very language dependent. as well.
exactly right. That's part of the problem with Big O, that complexity analysis stuff and data structures and algorithms is to some degree best taught in a language like C, because C is giving you nothing but what the computer gives you. And so the cost of every operation, because you can't do, nothing is given to you for free, more or less. In a language like Python, it gets more confusing. But I would say that, let's say we had a list. So if instead of doing it the way I did it, if I said, okay, we have a list, and that list is, I'm making a list out of a range of 10,000. So this is now the part that's creating that array, and it already has all the space. And then if I ask you, just give me the complexity or the space complexity for this part, you could say, oh, well, it's constant time because it's adding to an array, but that array already has that space. I mean, I would have to clear it out. I don't know. It's a little confusing without knowing exactly how it's done. So I guess short answer to that long thing is, if you didn't write it, you generally have to look it up. And it should be the standard guarantees for that type, but the devil's in the details. You'll never really know unless you do it. Unless you dug into the Python internals and said, this is how they're accomplishing that. And most likely that would involve learning C and reading the actual interpreter or compiler for Python. So it's beyond, that's another thing about Big O that's odd, which is you're not going to know with precision the Big O of something you didn't write. So it's always, and that's part of the reason why when you talk in a tech interview about it, it's not that mathematically rigorous. It's kind of this informal version of it. Because you could say okay, well, assuming list.append is constant time, I'm going to assume that because I don't know, but let's assume it. Then I can say that this is, time complexity n squared, assuming this was not 100, but rather based on the size of the list. But, space complexity constant. But that's only because we're saying, I'm making an assumption about how this works. And you can do that because you're not expected to necessarily know. And the interviewer can always say to you, oh, well, actually, I know that append is, linear time. So factor that in. So hopefully that helps. Yeah. The goal is that we just sort of build intuition around analyzing an algorithm. And the number one thing, if you don't remember anything else from today, is every time you nest a for loop, you're doing it that many n times. So if it was just a for loop, that's n times. If it's a for loop within a for loop, that's n squared. And for loops within for loops are often necessary, but that's also what's going to determine the worst case complexity, generally. All right. Any other questions, or we can just look at the time complexity.
There's one in chat.
Yeah, what? Oh, there's in the chat. Okay, let me check. Yeah, I believe, Daniel, you're right about that none times something thing. Yeah, and I appreciate it too, Drew. That is a thing, basically as programming gets more if most of us, including me, if we tried to be programmers in the 1970s, we would give up because it was incredibly frustrating to do it. Maybe we wouldn't. But basically, languages get more and more high level, which makes them more and more productive and easier for the programmer to think about. But as you do that, you get further and further away from the ground truth of how does it really work. And so it gets harder and harder to talk about this stuff. Like there's a language I really like called Haskell. That's a very academic language. It's one of the only pure functional programming languages, but part of the problem is that because of how it does it, it's so high level that it's almost impossible to do complexity analysis with it, because it has certain qualities that make it just about impossible to know how much effort really goes into a given function. Is the variable stored in memory if it is used like the iterator in a for loop like I and j is here? That's a good question. It definitely does exist somewhere in memory. There's no way that you can have a variable associated with, a letter. So I can't have the number 4 associated with the, phrase I, the identifier I, without that lookup living somewhere in memory. That said, declaring a variable will generally never count against you in complexity analysis because it's a constant time thing. You're creating one variable at a time. But yeah, everything ultimately does live in memory, including writing a function or calling a function. Everything that runs on a computer has to have some internal representation in the memory. So you see, we got.
I think my question there is more on the memory complexity side of it. So is it constant memory because you're replacing I every single time?
Yes, yes.
My question is kind of like, is it better for memory if you do, because kind of you could assign a variable to a certain operation, or you can chain all those operations together. So the computer just does all that computation at one time and assigns it to one variable. I'm wondering if there's really a gain of memory space on that. And maybe is it because what memories you're leaving in there longer throughout your entire program for a variable, as opposed to what you're just computing on one line and resolving immediately?
Yeah. So you're it sounds like what you're saying is like, if instead of saying like for I in range 100, for j in range 100, like in this case, I would, or let's say I had like a sum or something. I could say sum equals 0.
Maybe like your range 100 for the for loop. Are you creating the list with that range? Or are you only creating the list as you append it? Is that just because it's an iterator, right? So it's a different thing in memory. Is it something that persists? Or is it just because it does not persist, so we don't really think of it as creating a variable during the program?
The range part, or?
Well, yeah, because you're making something for the computer to be able to look up.
Yeah. No, you're absolutely right that if you get like technical about it and dig into it, you could say like, okay, well, for this to run, I have to run this. And imagine we said, instead of this, we said list of range 100. So this is actually going to create a list of size 100. And that has to live in memory. It will stop living in memory. It'll get like marked for deletion once this for loop is over. But for the duration of this for loop, this 100 element list will exist in memory. And that is, that is expensive on some level, especially as that number grows and grows and grows. Part of the reason this idea of range exists is that a range is not a list. A range is a much smaller data structure that looks something like class range def init, where the range really just has a starting point and an end point, and then sort of every time you call it, it'll just increment by 1. Does that make sense? As in, internally, if I make something called a range 1,000,000, unlike if I said list, of size 1,000,000, instead of having a list of 1,000,000 elements, this is ultimately represented in a much smaller way, where it's probably just holding on to the first element or the first, where the range starts, where the range ends, and then it has like, a next element function that'll bring you that next element. So just to see that, like if I typed into Python something like So I'm gonna say R equals range 1000, right? And then I'll say my list equals a list of R. And now if I ask for the, how do you do this in Python? Size, or I don't know that length is what I want. I want the amount of memory. Is Zainab here to remind me how I get the amount of memory in an object?
I think it's double under size of.
Okay, yeah. Wait, double under size, or
Under
it's,
of.
if
Yeah.
I did, you're saying like this,
Yeah, doesn't that give you the size of memory?
and then it's a function, or? Yep, okay, there we go. So yeah, my range is represented in 48 bits, I'm gonna guess. And that's somehow accounting for these various things it cares about. Like, it seems to keep track of the count, the index, the start, the step, and the stop. Whereas if I alternatively look at the size of my list, it's gonna be way, way bigger, because I actually have something at each one of those indices. It's not just a representation. So that's to that point that the more you dig in, the more you can actually answer a complexity analysis question well. Because like in this case, I am not like assuming that this was n as opposed to a million. The big O here is still constant time, because range does not get bigger based on n getting bigger. So for space complexity, we're still constant time. Whereas the minute I make it into a list, it's no longer constant time. Now it's space complexity n, because I created a list of length n in order to accomplish this. Yeah. But that is a good point to like zoom in on just, how it can be finicky to figure out the big O for when you're including stuff you didn't write, and you're always including stuff you didn't write. All right, so any other questions, or if we look at this website here, we can see hash table is kind of an important one, because hash table is the only one where you will get search in nearly constant time. You see, you get this little asterisk, because actually you cannot guarantee a big O of constant time for search. This isn't big O, rather it's average case, which I guess would be theta O, but no one really cares. We just talk about big O. But the asterisk is there to tell you that like the nature of a hash table is that like it's not exactly a worst case scenario guarantee, but it's close enough. And there isn't exactly a technical definition of close enough. We just probably don't want to get into it right now. But yeah, like if you're ever in a situation where you need to search and basically look up instantly, which you have some key and you automatically want to get the value of it. If you had an array, there's not a good way to do that. Like you have to look at each element and see if you found the right key, if you were just representing your key values as a tuple in an array. Whereas a hash table is the way to look something up nearly instantaneously. And it's because of its design. Like if you looked into how to make a dictionary, you would see, right, okay, that's how it's guaranteeing that. And it guarantees it using this hash algorithm. Part of the reason queues and stacks are nice are because for the things you care about, you're getting all constant time stuff, except for search in a stack, but that's got to be true for a queue too. Search can never be constant time. Yeah. So any other questions, let me know. I do think we could, this is a tough lecture. The good thing is that you're not going to use it right away, like at all. That's could be a good or a bad thing. You do want to get used to it though, because it's sort of a big O, for whatever reason, ends up being like the cherry on top of a tech interview. And that if you're given a problem and you solve it and there's time left, the person will ask you to analyze it in terms of big O. And if you can do that effectively, if you've solved it and you've analyzed it in terms of big O, and either you can say, I did it as well as I could, or that big O analysis lets you say, oh, I see how it could be done better. I just didn't do it that way, but now I know. That's basically a guaranteed pass because you solve the problem and are able to analyze your solution in a way that is objective and the other person can't help but agree with because you're speaking the same language. So big O is important for the sake of like this common language engineers can speak to say good or bad from an efficiency point of view. Yeah. I'm not going to let you go until 10:45. So just any questions. I mean, really just about anything in the program at this point. Well, we can work it into complexity analysis, but like, we've been doing this for a week now, the data structure stuff. It's a lot because if you really want to understand, all of this at a deep level, it takes a fair amount of time. And as you can see, like there's data structures here that we don't discuss. We generally don't discuss graphs or heaps or tries. We certainly don't discuss dynamic programming. There's all sorts of categories of interesting data structures, algorithms. But just if you have any questions about anything data structures or algorithms, let's do some of that now. Even the chat is empty right now. Okay, well, in that case, I am just going to open up that slideshow again. And we're going to jump to the best slide. And we're just going to look at it because this is the lesson essentially. Oh, there's a little website here. Let's click on it, see what it is. Big O cheat sheet. Oh, okay, yeah, here. This is insanely ugly and complex, and you wouldn't want to think about it this way, but yeah, this is perfect. Someone made a resource. Oh, they want you to pay for it. They want you to pay for it. That makes sense. But the core thing is that using these tools of time and space complexity, we can measure data structures and we can compare them to each other with this common language. And so we can say like, oh, I'm doing something that requires, as efficient a way as I can do deletion and insertion, and then everything else I can compromise on. And doing that, I say like, okay, insertion, or sorry, worst case is what we care about, insertion, deletion. Okay, so, a stack of queue or, a linked list would work and kind of nothing else would be ideal. And that's how you know that you care about that. Whereas like, let's say you said, I have to get, what's something that like, so like, it seems interesting. Like, I don't know much about a B tree or a red-black tree, but what they're saying is, well, if you have a situation where you want to do all those things, you want to access, search, insert, and delete regularly, we can get you log n times for all of those. We can't get you constant time for any specific one of them, but we'll get you log n for all of them. So that's kind of like a well-balanced approach. And it's just, even if you didn't know what any of these data structures were, just by knowing your use case, you could look at a chart like this and say, you might even discover something and say like, oh, wow, it really looks like, an ABL tree is right for us. And that just sort of gives you a direction to look. this chart says a lot. I don't know. But yeah, it looks like we're just about out of time. We can wrap up in a second. I hope this lecture was useful to you guys. Hopefully the assignments help elucidate it a little bit more. But either way, really just let this idea of complexity analysis kind of like gestate in your brain, and you won't think about it too much for a little while. And then once we get into the career prep portion of things and we're drilling leak code problems a little more, then you will think about it more, because basically first and foremost solve the problem, but after you solve the problem, look at your answer and objectively analyze it with Big O. But yeah, that's all I really have for you, I think. We have some slides here that you didn't see because they're hidden on purpose. But one of them is like this, for instance. It is math. If you want it to be hardcore, this is how you compute the Big O for a given function, but you and I both have trouble reading this, I bet. And this would be a case of like actually calculating it, and that's how we arrive at the actual answer. So just know that there is, if someone wants to get specific, they can, and that's how Big O values are discovered. Anything else hidden that we didn't see? No, that's it. Okay, that's all I have for you. You guys can go. You guys can get lunch and come back at what, 1:30 for you guys? I get confused because I'm off by an hour. 1:30 CST, is that right?
Correct.
All right, so enjoy your time off. Eat a lunch. Speak to you all in a bit.